Alright, welcome back. This is the 7th homework at the South Dakota School of Mines and Technology, thermodynamics. This is problem number 2. Homework 7 is associated with flash calculations using vapor-liquid equilibrium diagrams and being able to follow those pathways and be able to read those graphs. Okay, and so we've followed this path, we've defined this path. Now let's kind of see if we can't flesh out the details of this path so that we can use that information to do a mass balance with. Okay, and that's going to be the third part of this problem. Okay, so I've done that. Now it's saying, okay, what's the pressure, what's the liquid composition, and so on and so forth. So I've kind of made a little table over here to identify all the little points that I drew from the last problem. If you're curious what went on with the last problem, just watch the previous video. Okay, so let's look at A. So A was down here. So this was A, this was B, this was C, this was D, and then this was kind of like, essentially E was separating them. So this was like, E1, and this was like E2, and this was like F1 and F2. Okay, kind of thing. This was F2. I don't know what this was. Okay. Alright, so I kind of want each point essentially. So I probably should have so E1, E2, F1, F2. Okay, so what's the pressure? Okay, and I could do all these points one by one in terms of the pressure and all these other things. So we'll just do it as a point. Okay, so point A was down here. Okay, well, that one I can just kind of read off the problem first, 31, and it said the overall composition was 90%. Okay. When I look at the graph, okay, so A's down there, well, what's the liquid composition? It doesn't have one. Why doesn't it have one? Because there is no liquid. There is no liquid to be seen anywhere. There's nothing in the liquid phase. Now, when I'm on a line, I have a liquid composition because I have one drop of liquid, okay? It's not a lot, it's like, 6 molecules type of thing, but, I do have a composition, okay? Now in terms of, and so the vapor composition is the same as because it is all vapor, so it's Z, and of course the vapor fraction is either I don't have one because I don't have a liquid composition, or it's 100% vapor. We'll just say it's 100%. Okay. All right. Let's move on to B. I raise the pressure to 36. Okay, so that's another one where I just know the pressure. Okay. And the stream exits. Okay. So I just raised the pressure. Okay, well, as I said in the first one, I didn't change the composition, and so this is still 0.9. Now, other things may have changed, but it's still overall 0.9 because I haven't moved horizontally. So until I move horizontally, my Z is not going to change. Okay, now, do I have a liquid composition? Yeah, okay, now I do, because now I'm in the liquid region. I'm up here where it's liquid, and down here it's vapor. Okay, and so now this is 0.9, and this has no thing, and this is 0%. Okay, basically those swapped places. Very like, oh, well, why would you do that? Maybe there's another processing thing going on here, but I just want to track what's the compositions of stuff. Okay. So who knows why it comes in at that pressure? Who knows why it exits at that pressure? But that's what's going on. Okay. C. The pure component 2 is added to the stream until the vapor fraction is 16%. Okay. So for whatever reason, I'm adding in component 2. Okay. We said it moved here. We did some math. We figured out that Z needed to be about. We figured out from the last problem that Z needed to be about 0.8. Okay. Well, I know the vapor fraction is 16% because that's stated. I haven't changed the pressure, so that still should be 36. And to get 0.8, I had to find out that the x1 was 0.82 and the y was 0.7. And then it says the pressure drops to 35 kPa. Okay, so this becomes 35, obviously. Have I moved horizontally? No. And so my z should be exactly the same, no matter what it is. Okay. Did my x and my y change? Yeah, it did. I mean, I was up here, and my xy's were there, and now my xy's are here. So now I have to actually read my graph to figure out, okay, at 35 kPa, what are my x and y's? So if I look at those, okay, it looks like this is easily a 0.85. And then the other one is easily 0.75. I mean, I can just eyeball those ones. So it almost, I mean, I don't even have to do the math. I should do the math, but I don't even have to do the math to figure out that that's 50%. But let's do the math. Okay, so vapor fraction is equal to z minus x over y minus x, absolute value. Okay. And so I plug those in and I get 50%. Because I did that on purpose. Okay. All right, and then E I say I separate it. Okay, so I have a E1 and E2, which all have different things. Okay, they're still at the same pressure. Okay, they still have the same x and they still have the same y. They still have the same x and they still have the same y because I'm still at equilibrium and I'm still at the same pressure. If I know the temperature and I know the pressure, I have to know the compositions of both phases. I have to, if I know they're in equilibrium, which in this case, I do know they're in equilibrium. So because I know they're in equilibrium, and because I know the temperature and I know the pressure, I have to know all the compositions. It's just the way it works. And so these haven't changed. This is still 0.85. This is still 0.85. This is still 0.75. This is still 0.75. What's changed is my z. Because what is the only way I can change z? By moving horizontally, by changing the composition. And when I separate that, well, that specific stream has a new composition. Because it was all the liquid that was in the mixture. And we know that the liquid has a different composition than the vapor. Okay? But I was able to just separate them. And so I just have to make sure that these line up correctly. Well, E1 corresponds to the liquid, and so the liquid should match. And this one's a vapor, so the vapors should match. Okay. And because this one's all liquid, the vapor fraction is 0%, and because this one's all vapor, this one should be 100%. Kind of a no-brainer on that. All right, F1. The liquid is sent to a throttling valve. Okay, So F1, liquid is sent to a throttling valve to lower the pressure until one drop remains. Okay, well this is, so one drop remains, I do that. Okay, I look at the graph. Let's see here. That's about 33, I'd say. Okay. Has my liquid composition changed? Yeah, my liquid composition changed. Okay. Because, I was here, now I'm here, and so my liquid's way over there. So if I kind of look at that one, so 33, maybe like 0.92. However, this should be exactly 0.85. It's a funky 8. So 8, 5. Okay. Because this Z didn't change, but all my liquid is now vapor. And so these should be exactly the same. And these should be exactly the same. And I said there's only one drop remaining, which means I'm at the dew point, which means I'm 100% vapor. And the other, vice versa there on the other one was until one bubble remained. That means I'm at the bubble point, which means I'm a 0% vapor. And it's the same kind of thing. It's like, this becomes my liquid, 0.75. It's still 0.75 here. Okay, and now I just need to figure out my new y based on that one. Okay, well, oh, and the pressure, well, the pressure was about 37, and then when I read 37, okay, that's about 0.65 or something. But I just need to graph and just keep conscious of what's going on and what all my compositions are. And obviously, you know, the biggest important part is, you know, being able to map it. But once I map it, I just need to read the different points. Okay. But I know I should be drawing this right because these things should translate in that way.